Okay, so for our first class since, well, the whole world changed. I hope that all of you are managing, in spite of all the upheaval and uncertainty that we all have to deal with. So we're just going to try to keep going as best we can. Um, okay, so um, as a reminder, the low I know people are behind in homework, and I'm also behind in grading homework, which I plan to deal with pretty soon. Um, the lowest two homework assignments will be dropped. Something I mentioned in email. Um, so if it gets to the end of the semester and still behind, you can always decide to not do those last two. Um, the final. Um, okay, after only 1 minute, the uh, recording cut out. Hopefully, it doesn't happen again. So for the final uh, format um, as originally stated in the syllabus, just because the final was not going to be an in-class exam. Anyway, either oral, final, or coding project. A coding project, you can find methods for solving boundary value problems, which is the um, last topic of the course. Oral final, that would be comprehensive and or some kind of video conferencing technology. I don't really care which we use. I've used I use Skype with some and FaceTime with others. That's really up to you. And So since all of this is your choice, again for each individual student, um, oh, um, and all work has to be completed. Whoops, I shut down my browser. Um, all right, so May 6th is the last class. So, um, and everything, all coursework needs to be completed by, and I'll check the calendar here real quick, just to make sure I have the right day. Oh, okay. Um, yeah, May 14th, which is the Thursday. That's the Thursday of finals week. Okay, all right. Um, so whatever you have, homework or handling a final, however you want to handle it, um, everything must be due then because grades have to be submitted the following Monday on the 17th. I want to have time to do all the grading. Um, okay. Now, um, for today's topic, um, we're shifting to a different kind of problem, but we're still going to build on things that we've seen before. So, um, all right. So the kind of problem would be initial value problem for ordinary differential equations. So the general problem we'll consider um, is first order ODE of this type. On some time interval from some initial time t naught to final time capital T, um, and um, and the initial condition will be yt naught is equal to some given value y naught, and we'll be assuming that the problem is well posed and that the function f satisfies the appropriate conditions to so that this problem has a unique solution based on the existence uniqueness theorem. And the funny thing about this topic is, unlike, for example, solving linear systems, where you need to have a strong linear algebra background to be able to understand numerical methods for such problems. Differential equations is a little different in that the methods that you learned, the analytical methods you learned in a differential equations course for solving problems like this, like is a problem separable or is it exact equation? All of those kind of techniques do not play any role in the numerical methods that we're going to see. We do use Taylor expansion, for instance, but not typical differential equation solving methods. Okay. All right. So I want to explain before getting into any particular numerical method, how we go about solving um, these kind of problems in general. And I have to get my pages in order real quick. Okay. All right. Fortunately, I will not be going through many pages today. It's been crazy first day picking things back up. So first, what we'll be doing, using many different methods, is time stepping, time marching. Okay. So what we do is I'll use a subscript yn, which is an approximation of the exact solution y, which is a function of t, evaluated at time tn. So when I'm referring to y of t, y of some time t value, that's the exact solution. When I have y that is subscripted, that is the numerical solution. So we're going to compute the solution at times t1, t2. So at certain points in time, t sub I, so each time is equal to the initial time plus I times delta t. So delta t is a very important quantity for us. Okay, that is the time step, or the length of a time step. Now, for the purpose of this discussion, I'm going to assume that we're taking time steps of the same length. So we're solving we're solving the ODE at several equally spaced times. Now, that will not be true in general. In fact, some of our methods called adaptive methods that change the length of a time step in order to improve accuracy and efficiency. We won't be getting into that level of detail in this course, but I just wanted to make you aware of that. But we're going to make the assumption of equally spaced time values. Now, okay. All right. So what I'm going to do is, actually, I'm going to put this here. And in this chapter, we're going to see both one-step and multi-step methods. I'll be covering multi-step methods next week. Okay. All right. So, the idea is that one-step methods computes the solution at time tn plus 1 using only information from the interval just one time step length, Tn to Tn plus 1. Whereas multi-step methods, they go further back in time. So maybe back to Tn minus 1 or Tn minus 2. It varies from one multi-step method to another. So for this week, we're just going to look at one-step methods that use only this time interval and information about the solution over this time interval, or from values of f on this interval to advance from time Tn to time Tn plus 1. Okay, so one-step methods, they can be designed in many different ways, but a useful starting point is Taylor expansion of the exact solution. So if I evaluate the exact solution at time Tn plus 1, but I do a Taylor expansion around Tn, then the because the difference between these time values is delta t. Or actually, I don't want to use. Sorry, I goofed here. I'm not going to use delta t for the time step. For consistency of a book, I'm going to use h. Okay. Whereas when we're talking about partial differential equations, where we have spacing in both time and space, then it's common to use delta x and delta t to distinguish. But here we're only stepping in along one dimension through time, so I'm going to use h to refer to the time step. And that's a common notation in this field, h referring to the spacing. We've seen h used as spacing elsewhere, like for numerical differentiation and integration. So that notation will be consistent with that. Since those methods for approximating derivatives and integrals, both of them, we're going to need here. So for the Taylor expansion, we're going to have h times y prime at Tn plus 1/2 h squared, and then we'll have y double prime. And I'm going to stop the Taylor expansion at this point. Where the unknown point at c is between Tn and Tn plus 1. So that's just what Taylor's theorem gives us. But if I use the fact that y is the exact solution, and that is what I'm expanding here, okay. All right. Taylor's expansion of the exact solution. Okay, but y prime is equal to f of ty. So I'm going to substitute that in here. So that'd be f of Tn, y of Tn. All right, so the exact solution satisfies that. Okay. Now, so what I'm going to do is to obtain a very simple numerical method for solving this problem. I'm going to truncate the Taylor series. Okay. So if I just neglect this order h squared term here, so presumably that would be small, quite small if h is small, then I have this method, yn plus 1 is equal to yn plus, so now I'm switching to using the approximate solution rather than the exact solution that we see here, hf of tn yn. So now the exact solution satisfies this. The approximate solution, the numerical solution, will satisfy this. So this is the simplest time-stepping method we can imagine. That's Euler's method. Okay. So we want to know, how effective is this method? How bad is it that we neglected this third term in a Taylor expansion? So we need some way of evaluating whether a method such as this for solving this initial value problem is actually accurate. Because what this method is going to do is, keep in mind, the solution at time 0, so y naught, we go to the initial condition. This is your starting point right here. At time t naught, you have y naught. So then, we see how this method would work in that we substitute y naught in here and t naught here, and that gives us y1. Then we take y1 and substitute it in here and here. Here we have t1, which is this t naught plus h, so we keep adding h to the time value. And that'll give us y2, we substitute y2. So we keep substituting. So this method is applied for n equals 0, 1, 2, etc. And we require that y naught and t naught are those values have to be given, and that kickstarts everything else. So what is the way that we can evaluate a time-stepping method? So okay. So we say that this method converts if we have the following, that as a time step h goes to 0, and we look at the difference between the exact solution at time tn minus the numerical solution also at time tn. But we want to make sure that that this error is considered over all possible indices n. Now, what indices would you consider? Because we're time stepping. Keep in mind, we're time stepping from time t naught to time capital T. So the length of this time interval is capital T minus t naught. And then, if we divide that by h, then this value here, capital T minus t naught over h, that's the number of time steps that we're going to be taking. So we want the difference between the exact solution and numerical solution for all indices n to be, all these errors to be going to 0 as h goes to 0. So if we can somehow prove that this happens, then we can say that this time-stepping method converges, therefore it is an effective method. And then we can also answer questions such as, okay, so the error is going to 0, but how rapidly does it go to 0? We'll see that some methods converge more rapidly than others as h goes to 0. So during the course of this chapter, we'll learn about how to evaluate, both design and evaluate these time-stepping methods. So today I'm just going to show you Euler's method, and then we'll look at more sophisticated methods from there. Okay. So if we look at the equations, that the exact solution and the numerical solution satisfy. Okay. Now, I actually have these equations up above. I'm going to put them here together. So the numerical solution satisfies Euler's method. And then the exact solution satisfies this equation that came from Taylor expansion. Okay, and we have remainder term here. Okay. All right. Now, so before we go any further, that the function f is Lipschitz continuous. And we've seen Lipschitz conditions before, like in the case of fixed point iteration. It came up in that setting. So I'm going to repeat what a Lipschitz condition is. Just need the right page. Okay. So the Lipschitz condition is that the difference between... All right, so really it's just a Lipschitz condition in the y variable. Because notice the same t values are plugged in to f, these two equations, but the y values are different. And that's so we're actually going to need a Lipschitz condition in y. So if I evaluate f at two different points, same t value, but different y values, then Lipschitz condition requires that this difference in f values be bounded by some constant L that has a difference in the y values. Okay. All right. So, and L is the Lipschitz constant. Now, we saw this as a fixed point iteration on the function g from that method, where the Lipschitz constant had to be less than 1. We don't require that here. We just require that there at least be a constant that works, even if it might be large. Okay. Now, so I'm going to define the error for convenience. So En will be the numerical solution minus the exact solution at the time n is indicated by the subscript. So now the difference between these two left sides is En plus 1. And then if we subtract these equations, here we're subtracting these, that would be En. So now we have a relationship, we're going to have a relationship between the new error and the old error. But now we have to subtract these terms too. So we have plus h times f at Tn, Yn, minus f of Tn, y of Tn. Okay. Okay. And then I have this leftover term from the Taylor expansion, the Taylor remainder. All right. So now what I can do is if I take the absolute value of both sides and also use the Lipschitz condition, plus I'm going to make an assumption here that it's twice continuously differentiable. Okay. Now, the reason why I'm going to do that is that therefore the second derivative is continuous, time interval in question. That means that it will have both a minimum and a maximum on this interval. So now I have this, En plus 1 is less than or equal to En plus H, and then by the Lipschitz condition, this is less than or equal to L times the difference in these y values. But what are those y values? Yn and yftn. Well, but that difference is En, or the absolute value of En. So now I can put these, I can combine these like terms. So I can do the following. 1 plus HL En. And then this other term here, I can bound that h squared m over 2, where m is a bound on the absolute value of the second derivative. So now I have this relationship between the old error and the new error. So this gives me an idea of how much the error could possibly grow from one time step to the next. Okay. So now if I apply this relationship between the old error and the new error repeatedly, then I have this. En plus 1 is less than or equal to this from En, but then I use the same relationship to express En in terms of En minus 1. So I have 1 plus HL and I have, so I have everything I had before, and this was En, but now I'll have En is less than or equal to 1 plus HL En minus 1 plus, and again I'm going to have h squared m over 2. Okay. So that will get multiplied by 1 plus HL also. And I can do this one more time. So I can say En minus 1 is that is bounded by 1 plus HL En minus 2 plus h squared m over 2. Okay, so now what I want to do is let's clean this up here. So I have En plus 1. So I have 1 plus HL cubed En minus 2, which makes sense because between n minus 2 and n plus 1, that's 3 time steps. So I have 1 plus HL cubed. I decided 1 plus HL to the first power when I only had one step. But what about the rest of this? So this is going to be, notice we have every single other term I have has an h squared m over 2 in it. So I'm going to have h squared m over 2 times what exactly? Well, I have this one just by itself, so that's a 1. This one is multiplied by what's sitting outside the outermost square bracket, so 1 plus HL. And then this one is multiplied by this 1 plus HL and this one. So I'm going to have 1 plus HL squared. Okay. All right. So now, if I were to keep going with this, what would that give me? So I have En after going all the way back to E0. So that's less than or equal to 1 plus HL to the N E0 plus h squared m over 2. And now I have the sum 0 up to n minus 1. Because notice I had taken 3 steps from here to here, but I only had up to power up to 1 plus HL. Oh, sorry, my 2's in the wrong place. Should be out here. Only raised up to the second power. So that's why I'll stop at n minus 1. So I'm going to have 1 plus HL raised to the I power. Okay. So that encapsulates everything that we see here. So we have it to the nth power here. Every power from 0 up to that minus 1 is what goes here. So here I had a cubed here, but only up to squared here. So that is reflected down here. Okay. Now, E0 is 0 because we're using the initial value as a solution at time 0. So there's no error at time 0. So this term can actually be neglected. So now what do I have? I have this. But I can condense this because I'm going to have h squared m over 2. And then I can use a formula for a geometric progression. So this is a partial sum of a geometric series. So a formula for that is equal to, here, if I stop at power n minus 1, what I'd have up here is 1 plus HL to the n. So whatever power we stop at here, plus 1, and then minus 1, I could, whoops, sorry, I'm putting this in the wrong place. Okay, I want to put that down here. All right, and then down below we're going to have what we're raising to the power, so it's 1 plus HL, minus 1. Okay. Now, but the thing is, I have 1 plus HL minus 1. So I can cancel the 1s, and I'm left with just HL. Also, I have H down here, H squared up here. So I can cancel one of the H's. Okay. Now, I'm going to take this L, and I'm going to move it over here. And now I don't really need this to be a fraction anymore. Or I do need to put in parentheses. Okay, so now I have that. Now, 1 plus HL. Okay. Before I continue. So sum of geometric progression. This one's good to know things. As far as formulas go. Okay. Now, in general, if x is positive, 1 plus x is less than e to the x. Because 1 plus x are the first two terms in the Taylor expansion of e to the x. If x is positive, all the terms in the Taylor expansion will be positive. So we have that going for us. Okay. Also we have the following. if I take h and then n, h times n is equal to Tn minus T naught. That comes from a definition of Tn. Tn was defined to be T naught plus NH. And that is less than or equal to T minus T naught. Because Tn belongs to the interval T naught to capital T. It's never going to go past capital T. So we have this relationship. So I take advantage of all of these. I have hm over 2l. So this is less than or equal to e to the lnh minus 1 but n times h is capital T minus T naught. So it's e to the L T minus T naught minus 1. And now I'm done. So this is my bound on the error at time Tn. Now, what I want to do though is, like, if I so if the error at any time Tn is less than or equal to this, but notice everything here except h is a fixed constant. So it either comes from the problem statement or comes from the Lipschitz condition that we have by assumption on the function f. So this error bound goes to 0 so because the error goes to 0 as h goes to 0, Euler's method converges, and it is first order accurate since this error is big O of h. So notice the error is proportional to h raised to the first power. This contrasts with other methods that we'll see later, where the method is where the error is order h squared or some higher power of h. So we like those higher order accurate methods. So this is being a very simple method. It's no surprise that it's only first order accurate. But at least what we've established is that that it converges. Okay. Now, okay. So 2 important points I want to make about this error bound. First, so it does not properly take round-off error into account. So every time step, there is going to be at least some rounding error. And it's very difficult to quantify that, but even if we just assume there's just some generic floating point error, then the problem is we can go through this whole process again with a revised Euler's method that it includes the round-off error effect. But because it is not proportional to h, the round-off error can actually increase as h goes to 0. And one of the problems it's in this section, 12.2.1, I did not assign it, but it does state what the error bound is. So you'll see that it closely resembles it actually includes the error bound that was just shown here. That's like one term of it. But then there's an additional term, or actually two additional terms that deal with error. And we can see that whereas in this error bound you have h to a first power, but the round-off error terms have, one of them has h as a to a negative power. So as h goes to 0, that part of the error can increase. All right. So but what it also shows is that the error is actually going to 0 as starting h gets smaller and smaller. At first, the error does decrease, but there comes a point where it will increase after that if you continue to make it smaller. So there is a optimal h that you can use in this kind of situation. But what is the optimal h? It depends on the problem. It depends on you have a Lipschitz constant that bounds f. It depends on the constant m that bounds y double prime. So this is something to keep in mind here, is that using very small h value, you might think, oh, that increases the accuracy. But first of all, it's not necessarily true. Also, taking very small time steps leads to more computation time. So that's yet another reason why you don't want to use a time step that is incredibly small. So really, you don't get anything good out of that. Okay, so that's one point I want to make about this error bound. The error bound can be used to determine, and going back to this error bound here, how small h should be so if you have so you might say, oh, I want the error to be less than, say, 10 to the minus 3. I can set this less than or equal to 10 to the minus 3, and if I know something about how big f or its derivative can get, because that gives me an idea of a Lipschitz constant, this information is given in the problem, and I may not know how big the solution can get, but I might be able to have some idea based on the context of the application. And I can set this less than or equal to that error level that I want, and solve for h, because everything else in this fraction, m over 2l, this part here, if I can figure all that out, I can effectively solve for h. Now that's actually done in an example in a text, 12.2.1. But there's one caveat about that. This error bound is not sharp. What I mean by sharp bound is that the error is not only less than or equal to this value, but it's actually fairly close to this value. What we love to have is what's called a least upper bound, and we have nothing like that at all, because 1 plus x can be much smaller than e to the x, for one thing. Also, we're using this bound that applies to the second derivative, but in some places the second derivative can be much smaller than that. The Lipschitz constant is an upper bound on the derivative of f as well. So it could very well be that the true error at time tn is much, much, much less than this, in which case using this error bound to help select a time step might give you a time step that is extremely small, and you might be able to get away with a much larger one and still achieve the same level of accuracy. So an example in the text, I set the error level to be 10 to the minus 3, and I get an h value and use it, and I get an error that's around on 10 to the minus 11. So it's not something I would really recommend in practice. I mean, yeah, if you want as close to a guarantee as you can get, then sure. But you'd probably be wasting computation time. Okay, and that's a section. I think it's one of the best things about being in my office is that I have everything right here. um, the section that's not being covered in this course, but section 12.5 discusses adaptive methods that use a lot more sophistication to select a time step. Okay. All right. Now, what I'm going to get into, starting on Wednesday's class, a little more about one-step methods. First, how I can solve. I can use one-step methods in MATLAB, and also how you can code up one-step methods such as Euler's method. One of the homework problems for this section does involve coding up Euler's method, but what I'll do is I'll give kind of a framework what a MATLAB function for such a method would look like. And it's pretty similar from whether it's one-step methods, whether it's Euler's method or one of the higher order methods that I'll also cover on Wednesday. Those are called Runge-Kutta methods. Okay, so if anyone sends me homework questions, what I can do if it seems like they would be of general interest, like so not tied to your work specifically, but that's something I can also include when I record these videos. So be sure to keep homework questions coming. Reach out to me by whatever means you prefer, and so we'll get through these 6 weeks somehow. So. So these videos will be posted. I'll always record them during a time when our class used to meet, and then upload them shortly after. So like each Monday and Wednesday evening is when you should see these videos appear on the website. So until Wednesday.